Hello everyone. In this video, I wanted to make an explanation into how we can solve problems related to DC electric motors. Okay, in particular, I wanted to explain how you can analyze problems of the following form. For example, here we have an exercise that telling us that a DC series electric motor that is spinning at 4,500 revolutions per minute draws 3 amperes of current with a 120 volts measure at its terminals. The resistance of the armature windings measured with an ohmmeter when the motor is at rest on power is of 2.45 ohms. And they are asking us to compute how much counter electromotive force the motor is generated at 4,500 revolutions per minute. Okay. So based on this data, we want to compute the back EMF of the motor. Okay. And that is the meaning of the counter electromotive force, no, or counter EMF. Okay. So in order to solve this type of problems, well, we need to collect some data, no? For example, here we know that the speed of the motor is 4,500 revolutions per minute. We know that the motor requires a current of 3 amperes, okay? And also, we know that the voltage of the motor is 110 volts. The resistance of the armature windings measured with an ohmmeter when the motor is at rest and power is 2.45 ohms. Okay, so this is 2.45 ohms. So how much counter EMF is the motor generating? So based on this data, we need to know, no? So the idea is as follows. Let me share with you my screen. Just one moment. Okay. Just 1 minute. I wanted to share my screen. Mm, mm, mm. Okay. Okay. Now the screen has been shared, and well, I can show you the screen of my tablet, and well, I have annotated here the data of the problem. Okay. Here are the speed of the motor. Okay, the current that the motor requires, the voltage of the motor, and also the resistance of the armature. Okay, so based on this data, we know that for an electric motor, we have the following circuit. Now we have the voltage, okay, that in this case is 110 volts. And also we know that the armature of the motor has a resistance of 2.45 ohms. And we need to compute the back EMF, okay, of the motor. And also we know that the current that the motor demands is 3 amperes, okay? So based on this data, we want to compute the back EMF, okay? But this is relatively simple if we consider that, well, this is basically a DC circuit, and based on this DC circuit, we can apply the Kirchhoff voltage law, okay? So we apply the Kirchhoff voltage law to this equivalent circuit. We know that the equation is as follows. We have minus 110 volts plus 3 amperes times the resistance in the windings, that is 2.45 ohms, plus the back EMF voltage, and this is equal to 0. So if you solve this equation for the back EMF voltage, you will obtain that the back EMF voltage is equal to 102.65 volts. Okay, this is the back EMF voltage. So as you can see, Solving this type of problems related to AC circuits basically relies on the fact that we need to draw the equivalent circuit of the motor, okay? And typically, or in general, we can say that uh, the equivalent circuit of a DC motor consists of the voltage, okay? And in parallel, we have the armature resistance and the back EMF voltage, okay? And also, sometimes we can consider like the inductance of the motor, but remember that the resistance of an inductance, we measure that resistance in terms of the impedance, okay? And remember that the impedance of an inductor is basically J omega times L. But in this case, since we are working in DC, the frequency is zero, okay? So the voltage, sorry, the impedance of the inductor doesn't play a role in this type of circuit. Okay, because we are working in DC. So the only elements that are considered are the armature resistance and the back EMF voltage. So based on this, we can make another example. Um, so just one moment, let me share my screen. Okay. So here we have another example. They are telling us that we have the following permanent magnet DC motor. We have a permanent magnet DC motor. Also, they are telling us that the induced electromotive force is equal to 2000 volts. Okay, in this case, they are giving us the back EMF voltage. Also, they are telling us the speed of the motor in revolutions per minute, that is 1200 RPM. And we need to compute the electromagnetic torque developed at at an armature current of 15 amperes. Okay, so we need to compute the electromagnetic torque. But also we know that the armature current is of 15 amperes. We need to compute this electromagnetic torque. So the electromagnetic torque can be computed as follows. We know that the mechanical power, okay, let me share my screen, just one second. We know that the mechanical power is equal to, let me share my screen. No, I need to share the screen again, just one moment. The mechanical power of a DC motor is equal to the electromagnetic torque, no, times the speed of the motor. Okay, if we want to compute how much mechanical power the DC motor is providing, we can use this equation, no? But also we know that also the mechanical power can be computed by considering the back EMF voltage times the armature current, okay? So if we take into account the armature current and the back EMF voltage, we can compute the mechanical power. But also we know that the mechanical power is equal to the electromagnetic torque times the speed of the motor. In this case, we can equate these two relationships. No, we can say that the electromagnetic torque times the speed of the motor is equal to the back EMF times the armature current. And based on this relationship, we can compute the electromagnetic torque as the back EMF voltage times the armature current divided by the speed of the motor. In this case, we need to express the speed of the motor in radians over second. So, well, we can compute the electromagnetic torque as 2000 volts. No, this is the back EMF that the problem gave us. And also we know the armature current that is 50 amperes, and this is divided by the speed of the motor. Here we have the speed in revolutions per minute, okay? But we can convert these revolutions per minute into radians over second. So we know that 2 pi is equivalent to 1 revolution, and that 1 minute is equivalent to 60 seconds, okay? So we can use these conversions, okay, in order to convert these revolutions per minute velocity into radians over second. And with this information, we can compute the electromagnetic torque. That is 23 0.87 32 newtons per meter. Okay, so this is essentially the electromagnetic torque. Okay, but again, we can, well, in this case, you don't need to draw the circuit, no, because you have all the information. Okay, but we can use these relationships related to the mechanical power in order to compute this electromagnetic torque. Okay, but the key point here is that you can either use, sometimes it is better that you draw the diagram of the circuit, and sometimes you can use only the equations. Okay, so it depends mainly on how you need to compute. Okay, based on the data that the problem gave to you. So let's make another example, no? In order to make these points a little bit clearer. So, okay. So another example, in this case, we have the following exercise. They are telling us that the armature resistance of a DC motor is 0.5 ohms, no? So the problem is giving us the armature resistance, okay, that is 0.5 ohms. And also they are telling us that the current, no, the armature current is of 20 amperes, no? And that the voltage of the motor is demanding, well, is of 220 volts. And then the speed of the motor is 80 radians over second. And based on this information, we need to compute the back EMF and also the electromagnetic torque. So if we want to compute this electromagnetic torque, we need also these mechanical power relationships. But also we need to compute the back EMF. So in this case, we need to draw the circuit diagram. So to do that, let me share my screen, no, in order to explain this problem. So let me share the screen. And okay. So we need to compute the back EMF based on this data. How can we compute this back EMF? So we can draw the circuit, no? We have here the voltage source, that in this case is 220 volts. And in parallel, we have the armature resistance and the back EMF voltage. Okay, so the back EMF voltage is 220, no, sorry, no, this is not the back EMF voltage. And we need to compute this, and also we know the resistance, no, that is 0.5 ohms. And also we know that the motor is demanding 20 amperes. Okay, so we first need to compute this back EMF voltage so we can apply the Kirchhoff voltage law. So we need to add each of the voltages within this loop. So we have minus 220 volts plus the voltage drop in the resistor, that is 0.5 ohms times 20 amperes plus the back EMF voltage, and this is equal to 0. So if you solve for the back EMF voltage, you will notice that the back EMF voltage is equal to 210 volts. And well, I think that's it. So we have solved this circuit, and in solving this circuit, we can compute directly the back EMF voltage. But now we need to compute the electromagnetic torque. So you remember that the mechanical power delivered by this motor is equal to the electromagnetic torque times the speed of the motor. And also we know that we can compute this mechanical power equal to the back EMF voltage times the armature current. So we know the back EMF voltage, we know the armature current, and we know the speed of the motor. So we can equate or make equal these two expressions, okay? And we can solve this equation for the electromagnetic torque. So we have the back EMF voltage times the armature current, and this is divided by the speed of the motor, Remember that the speed of the motor needs to be expressed in radians over second. So we have the back EMF voltage that is 210 volts times the armature current that is 20 amperes. And this is divided by 80 radians over second. Okay. So the electromagnetic torque is equal to 210 times 20 divided by 8. So the electromagnetic torque is 52.5 newtons per meter. Okay, so this is the electromagnetic torque of the motor. Okay, as you can see, solving these problems is relatively easy. No, it is not too difficult. So we can make another example. Let me again share my screen. Let me go to my screen. Okay. So let's make another exercise. No? In this exercise, they are telling us that we have a 400 permanent magnet DC motor that takes an armature current of 100 amperes when its speed is 1000 revolutions per minute. If the armature resistance is 0.25 ohms, we need to calculate the torque produced in newtons times meters. Okay. So again, we need to compute the electromagnetic torque. So the electromagnetic torque, we can use the following expression. No, we have here, and let me share my tablet screen again. And now we can use again, we can perform a very similar analysis, okay? So we know that the exercise is as follows, no? We know that the voltage is 400 volts. Also, we know that the armature current is of 100 amperes and the speed is 1000 revolutions per minute, and the armature resistance is 0.25 ohms. Okay. And we need to compute the torque produced by the motor. So again, let me share my screen. Okay. Um, so I have here the data of the problem. We need to compute the electromagnetic torque. Okay. But in order to compute the electromagnetic torque, we need the back EMF. Okay. No, because we know that the mechanical power, okay, the mechanical power is equal to the electromagnetic torque times the speed. And also we know that the mechanical power is equal to the back EMF voltage times the armature current. So if we equate these two equations, we have the following relationship, okay? The electromagnetic torque times the speed is equal to the back EMF voltage times the armature current. And the electromagnetic torque is equal to the back EMF voltage times the armature current divided by the speed. And what else? Well, I think that we don't have any more information here. So what else we need? Well, we can compute the back EMF, the armature current, and the speed of the motor, to compute the electromagnetic torque, but we need the back EMF. So again, we can draw the circuit. Now here we have the voltage. There is 400 volts. And in parallel, we have the armature current that is 0.25 ohms. And here we have the back EMF. So also we know the current that is 1000 amperes. So based on this data, we can apply the Kirchhoff voltage law to this loop, and you will obtain minus 400 volts plus 400 amperes times the resistance of the armature, okay, plus the back EMF voltage, and this is equal to 0. So the back EMF voltage is 375 volts. Okay, so now we have all of the data to compute the electromagnetic torque. Okay, so we know the back EMF voltage, that is 375 volts, times the armature current, that is 100 amperes, divided by the speed of the motor, that in this case is 1000 RPM, times, well, we need to express this in radians over seconds, so we know that the 2 pi is equivalent to 1 revolution, and that 60 seconds, no, 1 minute, okay, 1 minute is equivalent to 60 seconds. So if we introduce all these values in your calculator, you can see that the electromagnetic torque is equal to 358.09 newtons times meter. Okay, this is the electromagnetic torque. And that's it. No? That's all the information that you need to consider, okay, for your analysis. So let's make one final example, no, in order to finish these exercises. Okay. So here we have a different situation, no? Because here we need to well, we have the following case, no? Just let me 1 second. Well, according to the problem, we have a shunt motor. Okay, so this complicates things a little bit, no? Because we need to consider other elements in the circuit. So for example, since here we are dealing with a shunt motor, okay, we cannot use the other circuit, no, that we have used previously, because the shunt motor, as you remember, we have the armature and back EMF voltage in parallel with the power supply, but also we have in parallel a shunt field, okay? That is basically a winding, no, in parallel to the armature. So we need to consider that in the circuit, or in the circuit analysis. So, well, I will annotate all the information first. First, we know that the voltage of the motor is 240 volts. Also, we know that the current that the motor is demanding is 30 amperes. And also, we know that the field winding resistance, the field winding resistance is equal to 150 ohms. And the armature resistance is equal to 0.4 ohms. And we need to compute first the armature current, okay, and also the back EMF voltage. So let me share my screen in order to tell you how you can tackle this type of problems. So let me share my screen, and I will I will share with you the process, okay? So here is the data of this problem. Remember that this is for a shunt motor, okay? So for a shunt motor, we have the following situation, no? We have the voltage of the motor. Also, we have in parallel the armature resistance, and we have in parallel also the back EMF voltage. But aside from that, we also have a shunt field, okay? And this shunt field has a resistance of 150 ohms. The armature resistance is 0.4 ohms, and the voltage is 240 volts. And also we know that the motor is demanding a current of 30 amperes. Okay. So based on this information, we can try to compute the armature current, that is this one, and the back EMF voltage. Okay. So we can compute first the current that is flowing through the field shunt, no? Through the shunt, through the field, through the shunt field, no? That is this one. And we can say that the current that flows through this shunt field is 240 volts divided by 150 ohms. Okay. The reason of that is that since these elements are in parallel, they are sharing the same voltage. So based on that, we can compute the current that flows through the shunt field. That is equal to 1.6 amperes. And also we can compute the armature current as 30 amperes minus 1.6 amperes. Okay, and this is equal to 20.4 amperes. And the reason for that is that we are applying the Kirchhoff current law. Remember that in this case, this current is entering this node and the other currents are leaving, okay? So based on that, this fact, we can compute the current that flows through the armature, okay, by applying the Kirchhoff current law. So I will express this in this section, no? We know that the 30 ampere current is entering the node and the current that is entering should be equal to the current that is leaving, that is the armature current, plus the current in the shunt field. So I can solve this for the armature current, and this is equal to 30 amperes minus the current in the shunt field, okay? And based on this, I can compute the armature current as, well, this value, no, 28.4 amperes. And, well, we know the shunt field current, that is 1.6, so I am basically substituting this value into this relationship. And with that information, we can also apply the Kirchhoff, okay, the Kirchhoff voltage law to this loop, okay? So if we apply the Kirchhoff voltage law to this loop, we have minus 240 volts plus the armature resistance times the armature current plus the back EMF voltage, and this is equal to 0. So we have that the armature resistance is 0.4 ohms times the armature current, that is 28.4 amperes, and this is equal to 0. So the back EMF voltage is 228.64 volts. Okay, and that's it. No? Now, what else? So this is the back EMF voltage. No? So we have finished the problem. So you can see that these problems related to the to shunt motors, no, are a little bit more complicated because the circuit is a little bit more complex. Okay, but again, you can use the Kirchhoff voltage law or the Kirchhoff current law in order to solve for all the variables of the circuit. Okay, so I think that that's it for this video. I hope you like it and see you later.